All right, so Unit 1, Day 1, sets of numbers in interval notation. Numbers were created out of necessity. Different numbers belong to different subsets of numbers. Okay, so we're going to be talking about numbers that we've been working with since we were little. And we're going to talk about all the types of numbers in the real number system. Now, before we do this, I want to make sure that we understand what sets are. So let me go ahead and just scroll down and use this blank space here. So this was covered in geometry, but I'm not sure if you remember this, but you have, let's say, a container full of elements, right? And let's say that within this set, you have the city of Austin, the city of Dallas, the city of, let's say, San Antonio. And if you can see what's going on here, we basically have what? Where are these cities from? Well, we know that all of these cities are part of Texas, right? So Texas contains these cities here that we know and love, right? And, well, if you have San Antonio, Dallas, Austin, and Texas, where are these located? Well, we know that all of these things here are located in the United States of America. Okay, so basically what I'm trying to say is, okay, you have Austin, Dallas, and San Antonio. They're part of Texas, and Texas is a state, and that is one of the states of the United States of America, right? So USA contains Texas, and it also contains Austin, Dallas, and San Antonio. Okay, so that's basically the gist of sets. Okay, so we're going to use that idea and then apply them to what we're going to be talking about very, very soon. All right, so we're going to go ahead and move on to sets of numbers now. We're going to discuss all the numbers that you've seen in life. The first set of numbers I want to talk about are the natural numbers. So the natural numbers are positive whole numbers, such as 1, 2, 3, 4, and so on and so forth. Notice with the natural numbers, there are positive whole numbers. There are no decimals. There are no fractions. There is no zero. And there are no negative whole numbers. So the natural numbers are just pure vanilla whole numbers that are positive, right? So these are natural numbers, but if I were to go up and include the idea of nothing, right? These are what we call whole numbers. So whole numbers contain the natural numbers and the idea of zero. So again, with natural numbers, no decimals, no fractions, and that's also the case with whole numbers. No decimals, no fractions, and both of these do not have negative whole numbers yet. But we're going to go ahead and introduce them as we talk about integers. So integers contain the natural numbers and whole numbers. But they also talk about negative whole numbers. So -1, -2, -3, and so on and so forth. So these are integers. Okay? So now what we're going to go ahead and do is talk about what these sets are under. They are under rational numbers. You probably haven't heard of that word before, but rational numbers are all integers. So I'm going to write all integers. Rational numbers are fractions. So if I can express something as a fraction, then that is a rational number. So let me go ahead and just detail what's going to go next to this word here. So fractions are going to be in the form a divided by b, where a and b can only be integers. Okay, and I'll talk about more about that when we do some examples. So rational numbers are all integers, can be expressed as fractions, and they can have terminating decimals. And they also can have repeating decimals. So here are some examples of rational numbers. So, examples. We can say -4. -4 is an integer, so that's okay, and I can rewrite that as -4/1 if I wanted to, so it's a rational number. I can also say 0. I can say 4, or I should say +4, right? I can say 1/2, and now look, 1/2 is a fraction, and this is my a over b, the thing that we talked about over here, right? So 1 is an integer, 2 is an integer, so if I put that all together, I have 1/2, which is considered a rational number. I can also say 0.45, and 0.45 is a decimal. It's a terminating decimal because it's not extending, it stops at 5, right? So this is an example of a terminating decimal, okay? I can also say 0.333 and so on and so forth, right? This is considered a repeating decimal. Repeating decimal, okay? So that's okay because I can express this into a fraction. All right, so 0.333 repeating, right? That's basically 1 divided by 3. 0.333 and so on and so forth can be changed into 1/3, and 1/3 is a fraction. I can express that as a over b, where 1 is an integer, 3 is an integer. Now with 0.45, I can math enter this, and that's going to give me 9/20. 9/20 is a fraction, 9 is an integer, 20 is an integer. Therefore, this 0.45 is an example of a rational number. Okay? Now, moving on, what happens if we don't have numbers that are rational? Then we call them irrational. Irrational. Now, irrational numbers are numbers that cannot be expressed as fractions. Irrational numbers can contain non-repeating decimals. Irrational numbers can also contain non-terminating decimals. So some examples of irrational numbers are 0.71456823 and so on and so forth. Look, we have non-repeating decimals, and this decimal isn't going to stop. It's going to keep on going forever. So this is considered an irrational number, and if I wanted to, if I input this into my calculator, well, this is not the full thing, right? There's more, but if I was able to put everything into the calculator and do that math enter trick to see if it's a fraction, well, you're not going to get a fraction. You're going to get this big decimal. Okay, so this is considered an irrational number because I can't express this into a fraction. I can also say the same thing about the symbol pi, right? Pi is 3.14 ... It's non-repeating, and it isn't going to stop. It's going to keep on going forever. So let's go ahead and try this with my calculator real quick. So if I press second and this caret sign, I get that pi symbol. I hit enter, and this is the result that you get. Now what I'm going to do is I'm going to see if I can turn this into a fraction. Math enter, and then I get an add. But the idea here is to see if this pi can be turned into a fraction without me saying pi over 1, okay? Let's try that again. So I press second, caret sign, I hit enter. Then I'm going to take the result and math enter that. So look at that. Once I math enter this, in order to see if I can turn this into a fraction, I don't get a fraction. I just get the same result as above, right? So this symbol here, or pi, is an irrational number. I can also say the same thing about the square root of 2 and the square root of 5. Well, the square root of 2 is 1.4142135624 dot dot dot. And it's just the same idea as these two here. You can't turn this into a fraction. The square root of 5. What about the square root of 5? Well, that is 2.23606797775 dot dot dot. And you know the drill with this type of thing here, okay? So those are irrational numbers, and these are all rational numbers. But all of these numbers, we're going to go ahead and conclude these numbers that we're working with here are all part. So all of these numbers are part of the real number system. All right, so let's take a look at some examples here. I have example 1, identifying subsets of numbers, decide which subsets each number belongs in. I have -6. Now, -6, is it a natural number? Well, if we look at the natural numbers, they only contain positive whole numbers. This is a negative number, so it can't be natural. Is -6 a whole number? Well, whole numbers only contain 0 and the natural numbers. So no, this can't be a whole number. But is -6 an integer? Well, integers contain 0, the natural numbers, and the negative whole number. So yes, I can definitely say that this is an integer. Is this number rational? Well, I can express -6 as -6/1. So we have -6 being an integer, we have 1 being an integer, and with those two numbers, I can create a fraction. So therefore, yes, -6 can be rational. So if a number is rational, then it cannot be irrational. So I'll leave this one blank. So it's either one or the other when it comes to rational numbers and irrational numbers. And then, yes, -6 is part of the real number system, right? Because all the numbers that we've been working with here are part of the real number system. Number 2, 5/6. 5/6, is that a natural number? No, because it's a fraction, so we can't say yes for that one. Is it a whole number? No. Remember, whole numbers contain 0, 1, 2, 3, 4, and so on and so forth. There are no fractions. There are no decimals. Is it an integer? No, because integers only deal with 0, positive whole numbers, and negative whole numbers. Is it a rational number? Yes, because this right here is my A, and this is my B, right? 5 is an integer. 6 is an integer. Well, it's already expressed as a fraction, right? So this is a rational number. Since this is a rational number, it can't be irrational. And then lastly, 5/6 is part of the real number system. So yes, I can go ahead and check that off. The square root of 7. All right, so let's see. Square root of 7. I'm going to do a little test real quick. I'm going to have my calculator on the side. But first of all, is it a natural number? Nope. Is it a whole number? Nope. Is it an integer? Nope. Is it a rational number? So that's what I'm going to use the calculator for. I'm going to press second, x squared, put 7 under the radical, and then this is my result. It's a decimal. Okay? So let's see if I can change this decimal into a fraction. I cannot. So therefore, this is not a rational number, but this is an irrational number. And, of course, it's part of the real number system. So whenever you're asked if it's a real number, typically you will just say yes. Okay? All right, pi. Well, we already talked about pi, right? It can't be natural, it can't be whole, it can't be an integer, and it can't be a rational number. We already talked about it, right? Pi is irrational, and it's a real number. Number 12, it's a positive 12. Is it a natural number? Yes. Is it a whole number? Yes. Is it an integer? Yes. Look, we're looking at these examples and comparing that to 12. So that's why I'm checking these, checking the first three things off. Is it a rational number? Yes. I can change this into 12 over 1, where 12 is an integer and 1 is an integer. So it's a rational number. And since this is a rational number, it can't be irrational, right? So I can't put a check mark for that. It's one or the other. And is it a real number? Yes. So that is how you identify subsets of numbers. All right, so now what we're going to do is talk about interval notation. Now, interval notation is going to be important for this course because we need to represent inequalities and graphs on a number line. So here, inequalities are the symbols that you know the greater than symbol, less than symbol, greater than or equal to, and less than or equal to. Now, first bullet point here. It says the greater than and less than mean we do not include that value in the solution set. However, if we have a greater than or equal to and less than or equal to, we do include that value in the solution set. So here are some examples on what I'm trying to say. So if we have something like x is greater than -2, well, what numbers are greater than -2? I can think of, let's say, -1, 0, we can also say 1, 1.5, 2, and so on and so forth. Those numbers are greater than -2. But what if I said that x is -2? Is -2 greater than -2? No. This is only true if they were equal to, if -2 was greater than or equal to -2. But in this case, we only have the greater than symbol, so we do not include -2 in the solution set. Okay, so let's take a look at this example here. We have x is less than or equal to -2. I can say -3, right? -3 is less than -2. -4 is less than -2. -5.625 is less than or equal to -2, right? So those values are going to be part of the solution set. But what if I said -2 is less than or equal to -2? Is that true? Yes, because -2 is equal to, that's why we have that little sign below the less than symbol, that, dashed line there. That -2 is less than or equal to -2. So we do include -2 in the solution set. And then here we have something like this. We have -5 is less than x, which is less than or equal to 4. So if I said, let's say, 2 for x, then that's going to be part of the solution set. If I said 2.5, that's going to be part of the solution set. If I said -4.5, that's going to be part of the solution set. What if I said -5? Is -5 less than -5? No. So that isn't going to be part of the solution set because we just have a less than symbol. If this was less than or equal to, then sure, we can be, or that number can be part of the solution set, right? But what if I said 4? Is that part of the solution set? Well, yes, -5 is less than 4, and 4 is less than or equal to 4. So yes, that's going to be included. It's going to be part of our solution set. So I keep saying part of or not part of the solution set. We're going to go ahead and talk about that here. So on a number line, an open dot means the number is not included. So open dot means the number is not included as part of your solution set. So if I had something like this over here, x is greater than -2, well, -2 is going to be the main character, And above the -2, I need to put an open dot, not a shaded dot, or not a closed dot, just an open dot above -2. And then on that number line, I need to determine what numbers are greater than -2, which we will shade to the right for, right? So like 1, 2, 3, 3.5, and so on and so forth. This is going to go towards positive infinity. Now, on a number line, a closed dot means the number is included in the solution set. So here I have -5 is less than x, which is less than or equal to 4. Well, looking at -5, this has a less than sign, so this is going to be an open dot. And this 4 is my other main character, and next to it has a less than or equal to, so it's going to have a shaded dot. That number is included because look, if I let x be 4, 4 is less than or equal to 4, so we're going to shade that, and it's going to be part of the domain here. So now within this interval, we're going to shade between these two dots here. Okay, so hopefully that makes some sort of sense. Now, some other things that we need to know about interval notation. We always write intervals from smallest to biggest. And then we only write the beginning and ending numbers in the interval. Okay? Now, this is important here. We have the square brackets. When we want to include the numbers as part of the solution. We have the regular brackets or regular parentheses when we don't want to include the number as part of the solution. Now, if the interval does not have an ending point, then we use -infinity or positive infinity as one of the endpoints. And we always use the regular brackets or regular parentheses around -infinity or positive infinity. Okay, so we're going to go ahead and look at some examples. All right, so number 5, we have an inequality, and we're going to be asked to write the interval notation and graph the number line. So x is greater than 11. One thing that I like to do is start with the number line here if I'm given the inequality. So I'm going to draw my number line, and the main character here is 11. And since we have a greater than sign, that means we're going to have an open dot above 11. So let's think of some numbers that are greater than 11. Well, I'm thinking 12, 13, 14, 14.5, 14.56, and so on and so forth. So the question here is, where do I shade? Do I shade to the right or do I shade to the left? Well, I'm going to shade it to the right here. Let's use a different color. There we go. And it's going to go towards infinity. So this arrow means we're going to be extending forever in one direction, right? So the interval notation is this. I start with 11. I'm reading this from left to right, by the way. I'm going to start with 11. And then where is it going to? It's going towards positive infinity. So infinity. And since 11 has an open dot, we use a regular parentheses for that number. And then since it's going towards infinity, for that one, as we said before, we just use regular parentheses for that. So I am going to close this with a regular parentheses. And that's how you write your interval notation for number 5. All right, so now we're going to go ahead and look at number 6. We have x is greater than or equal to 2. Draw my number line. 2 is the main character. This has a greater than or equal to symbol, so we're going to have a shaded dot. And then I'm going to determine where I'm going to shade. Well, since this is a greater than or equal to, let's think of some numbers, 3, 4, 5, 5.2, and so on and so forth. That means we're going to shade to the right here. So now I'm going to write my interval notation. We start at 2, and it's going towards positive infinity. 2 is included, so we're going to have a square bracket. And then For infinity, we just use a regular parentheses for that one. All right, so number 7, we're actually given a number line this time. So let's just determine what the heck is going on. So it seems like this 100 is included and it's shaded to the left here. So that implies that all of these values which we represent as x, is less than or equal to 100. And I say less than or equal to because we have that shaded dot above 100. So now let's go ahead and write our interval notation. So we're reading this from left to right. It's starting from negative infinity, but stops at 100. So then since we have a negative infinity, the best parentheses is the regular one for that one. And then for 100, we close that with a square bracket. All right, so hopefully that makes sense. Okay, so we have this right here. We have -3, 4. There's a regular parentheses next to -3 and a square bracket for 4. So let's figure out how we represent that. I'm going to go ahead and draw my number line first and then get right into the inequality. So let's draw the number line. My main characters are -3 and 4. -3 has an open dot and 4 has a closed dot. So we're reading from left to right. It doesn't seem like we have any, or I should say we don't have infinity involved and we don't have negative infinity involved. So it's just all the x values between -3 and 4. So when I write my inequality, I start with -3 and then end with 4. So what does the shaded region represent? It represents all the x values. So -3 is less than x because it's an open dot, and x is going to be less than or equal to 4 because we have a shaded dot. So that is how you represent the inequality for number 8. Now number 9, we have a -5 less than or equal to x, which is less than 1. So I'm going to go ahead and draw my number line. Our main characters are -5 and 1. So looking at -5 here, it's a closed dot, and then 1 is an open dot. So I'm going to shade between the two numbers and then write my interval notation. So it's -5, 1. There's a square bracket for -5 and a closed parentheses for 1. And then number 10, we have x is less than or equal to -3, or x is greater than 3. So I'm going to go ahead and draw my number line. Here's -3. Here's 3. -3 has a closed dot, and 3 has an open dot. So if I'm looking at x is less than or equal to -3, well, we're going to be shading to the left of -3. And if I look at x is greater than 3, then we're going to be shading to the right of 3. So now what we're going to do is write our interval notation, and we're reading this from left to right. So here, we're starting at -infinity, right? So we are going to write -infinity, -3. And then for this one, well, there's nothing between the -3 and 3. So I can skip this region and start with 3. So first thing, we have -infinity, -3. We write or because that's what we have here, or 3, comma, and then it's going to go towards positive infinity. Okay, so now let's go and finish these things off with our parentheses and square brackets. -infinity gets a regular parentheses, and -3 gets a square bracket. So this 3 gets a regular parentheses, and this positive infinity gets a regular parentheses as well.